Okay. Yes. Yes.
Then like the idea is that like, if you have two masses and gravitational wave comes, they will just metric changes, so it moves everywhere. Essentially, I'm just thinking that.
Yes.
So it's like they are being displaced and you're giving the usual notion of energy.
That's right. Yeah.
So
Yeah.
that's it.
Yeah. Exactly. So in this way of organizing things, right, you lose manifest general coordinate invariance, right? Of course, the general coordinate invariance is there because implicitly is the same equation that you are rewriting. Okay? You lose manifest general coordinate invariance, but the energy momentum conservation becomes simple to understand. Yeah, because it's the usual energy momentum conservation that we have in normal electrodynamics, for example.
Can we expand it around something else? Say, instead of beta nu,
Yes.
then whatever we get on the right hand side will be the del mu of that, d mu of that, but the d mu is the ADS d mu.
Exactly. That's right.
So it can be.
Yeah, you can do it in general background also. Yeah, you have to choose, I mean, what background you want to expand around, and you use a D of that.
When we expand it out, we put the linear terms on the left hand side and all the non-linear terms on the right hand side.
Yes.
There is no T mu, like when we are dealing with at the detector area, there is no T mu. So
Yes.
what is physically when we average it over T mu? What is it physically? Is it really related to the energy of the transition?
Yes, indeed. So in the detector, there is no matter source, but when the gravitational wave is passing through the detector, it of course is carrying energy, right? But what enters the formula, right, the energy conservation is the total energy integrated over the whole surface, right? But just like in electromagnetic wave, right? You think it's exactly analogous to electromagnetic wave. So when the electromagnetic wave passes through, it actually does carry energy, right? And you detect the effect of that.
Yeah, but my confusion here is we are only taking the higher order terms of the amplitude.
Yes.
But actually what we are detecting is this h mu nu.
Yes, that's true.
Yeah, but no, not the higher orders. Or are we detecting a total thing?
No, we are detecting h mu nu. Yes, indeed.
First order.
That's right. Yeah. Yeah.
Okay.
I mean, if you had a way to measure the flux, right, you could detect the higher order terms also. Right? It's just that we don't detect it, we directly detect h mu nu.
Okay, we detect that with the linear order.
Linear order, exactly.
And the way we define energy is not, for example, in electromagnetism, when we detect electric and magnetic fields, we say the electric and we somehow have E square plus B square kind of thing.
Exactly.
But here the terms which is coming is in the higher order, right? In the T mu
H square, right? Which is the same as E square plus B square. Quadratic, right? Quadratic in the fields. Here the point is there are also higher order terms, right? But there are certain quadratic order terms, right? And the formula that I gave for the energy of the gravitational wave is at the quadratic order.
And at the near to the detector, the sourcing is still done by the nonlinearity in the field. Like the GW propagation is happening. For example, if there is no T mu, it is happening out of the nonlinear order. Right?
Yes, but the point is that what you detect, right? You detect h mu nu, right? So which is like because h mu nu stretches, right? In electromagnetism, for example, if you had placed an electron, I mean that's not the way you normally detect electromagnetic wave, but you could have detected electromagnetic wave by placing an electron in the path of the wave, and the electron will oscillate, right? Because the electric field will oscillate. Right? So what we detect in gravitational wave detector is analog of that. How the particle is moving, right? Here, instead of looking at a particle motion, you look at the stretching of the detector. Right? So you can detect, in principle, also the power, right? In electromagnetic wave detection, right? Sometimes you just look at the total power that is being absorbed by your detector, right? Which measures basically quadratic part. Right? But if you had an electron, if you could place an electron and study its motion, you could just directly calculate, observe the linear part. right? Similarly, if there is a way to measure the energy flux of gravitational wave, you could have measured the quadratic part, right? And I would agree with what you get from a linear measurement. Okay? Just that the energy that is carried in the gravitational wave is so small, right, that it's not clear how to actually measure the energy that passes through us when the gravitational wave passes through us. But certainly there's an energy flux which is passing through us when the gravitational wave passes through us.
Regarding the measurements, we have some eta mean in the background flat space on which there are some perturbations.
Yes.
So this is not clear to me. How are we exactly measuring only the first order? It should be like the combination of first order, second order, everything.
Yeah. But it's just that the h mu is so small, right, that higher order terms are negligible, right? H mu is like 10 to the minus 21 or 10 to the minus 22, right? That's the kind of effect we have, right? So certainly higher order terms are much you can ignore.
Assuming that you're in flat space, gravitational wave is like something else. It's like waving this flat space which comes.
Yes. You can think of it that way, right? that is, you have flat space and the gravitational wave is just passing through us. Yeah. The point is, okay, experiment of course doesn't care about how you describe the theory, right? It just cares about what you measure. But what I'm saying is that while it is true that the gravity encodes the geometry of space-time, you can also think of this as just a regular field theory, where h mu is a field, right? H mu plays the role of a mu, for example. Flat background. Yeah, on eta mu, right? That's what you do in electromagnetism, right? The metric is fixed, eta mu, and you have a field mu, right, which fluctuates around that. The same, you can take the same viewpoint, right? It's just that if you take that viewpoint, then the geometric picture is lost, right? But as far as calculations are concerned, you can do the calculation without worrying about geometry. Yes, exactly. Right? Because we are in a region where the deviation from eta mu is very, very small.
When we have total 10 independent the case transformation to that just 2 independent poles. When I asked you about the 6 different polarizations, you said about in medium this can happen. But like the alternative theories of gravity, independent polarization like this vector modes.
Yeah, but you are not discussing alternative theory of gravity, right? Just within Einstein gravity, right? It's not that those provide independent degrees of freedom. Okay? Just like in electromagnetism, right? The things which you normally set to zero in absence of matter, right? Those things are not zero, but they get fixed by the matter source, right? They are not independent degree of freedom. So the number of independent degrees of freedom still remains 2. Right? Something similar happens can happen for gravity, right? That some of the things that you have set equal to 0 are not 0, but they are fixed by the matter source. So the vector modes, etc., are there, right? But when you study cosmology, for example, you have to deal with the vector modes, but they get fixed in terms of the matter.
Regarding this expansion around general, so the equations that I will finally get that I guess everywhere we had del u, we will get d, where d is the covariant direction.
Exactly.
Now, so in that case, what sort of coordinate covariance are we left with? Just like here, you are left with Lorentz.
See, you have the full yeah. So then it depends on the symmetry of the background. If the background has certain symmetries, that we will see in the equation of motion.
But doesn't that equation have the full?
Yes, it of course has the full general coordinate invariance, right? But that requires, it's not manifest, exactly.
It's
not manifest. When you expand, just like when you write eta mu plus h mu, right, and write the equation for h mu, It's not that you cannot change the equation. So clearly you have the full general coordinate invariance. Right? It's not manifest. Only the Lorentz symmetry part is manifest, right? Lorentz and translation symmetries are manifest.
But as I said, we will have covariant derivatives with respect to the background.
Yes.
And if I assume that under coordinate transformation, the background matrix changes the usual way.
Yes.
Then don't these equations have manifest general covariant?
No, because covariant derivative is not with respect to the general background, but only in the specific background. See, in fact, flat space, right? The ordinary derivative is the covariant derivative. So I could have written covariant derivative, right? That's the same as ordinary derivative. But you don't have manifest general coordinate invariance when you split it this way. Yes, so just because you have a D doesn't mean that you have the manifest covariance, right? You have to know what that D is. Right? Because in flat space also the ordinary derivative is D. Right, in that background. Because gamma is 0, right, in flat space.
In the initial years of calculation, like people are really confused about what the coordinate are. It's very physical.
Well, yeah, but the point is that derivation, of course, came much later, right? I mean, so yeah, I mean, the point is once you have a new equation, right, you don't even know how to, deal with this property, right?
So how does it really come this coordinate?
Because there is a coordinate change that is allowed, right? And you have to ask if whatever effect you are finding, right, is a result of coordinate change. Right? For example, I mean, we saw this k mu xi nu plus k nu xi mu kind of modes, right? Those also solve all the equations, right? Those are not physical, right? So you have to understand how those are related by coordinate change, right? Now the way I have presented it, it becomes clear, right? Because now we know how to properly deal with these equations. But in the early days, right, it was not clear how exactly one should deal with these equations, right? What is coordinate effect? What is a genuine effect? Any other question? I think what really settled this is when people actually showed that these gravitational waves actually carry away energy, right? Because whether that binary orbit, right, whether the period is increasing or not, that's something which is not a coordinate dependent statement, right? You measure the period and you see that it's increasing. So once we know that these gravitational waves actually can carry away energy, right, then it becomes clear that it's not just coordinate. Okay, so today I'll just finish the subject of gravitational wave by discussing the last topic, which is the circular polarization. Again, we will study this in analogy of electromagnetism. So let me explain what happens in electromagnetic waves. So in electromagnetic wave, circular polarized waves are eigenstates of rotation around the direction of propagation. Okay. So let me explain what this means. So let's suppose that you have two vectors. These are the two independent polarization vectors, right? Okay. This is if the wave is propagating along third direction. Okay. So you can take a general linear combination of these two. Okay. So general linear combination will be something like 0, U1, U2, 0. And then you can ask, how does it transform if you make a rotation along the third axis, right? Which means a rotation in the 1-2 plane. So under rotation by theta, in 1-2 plane, that's the same as rotation in the along the third axis. We have U1, E2 going to is this clear? Right? This is the rotation matrix, right? In the 1-2 plane. Theta is the rotation angle. And then the question is that to get a circularly polarized wave, what we need to do is to choose U1, E2 to be an eigenstate, eigenvector of this matrix. So the eigenvectors of this matrix, so let's call this matrix M. So this will be also appear later. So the eigenvectors of M are 1i and 1 minus I. This I'll not do, you can easily check with eigenvalues. Is this okay? Right, and this is what we call the circularly polarized wave. Right and left circularly polarized wave. So what we want to do for gravity is to find analog of this. So for this, let's recall that the gravitational wave is can be characterized by two polarizations. One for which U11 is equal to minus C2, right? The other one is U12 non-zero, others are 0. Okay. So if we take a general linear combination of these two polarization tensors, okay, then we can write this. So in gravity, a general linear combination of two polarization tensors it can be written as U11, U12, U12 minus U11. Okay, let me call this E. This is only in the 1-2 plane I have, right? Because others are 0 anyway. Because instead of writing a 4x4 matrix, I'm just writing a 2x2 matrix, right? Because the rest of the elements are 0. So the idea is that you have to take appropriate choice of U11 and U12, right, which means particular linear combination of these two polarization tensors, which are eigenstates of rotation. But you have to understand what you mean by eigenstates of rotation, right? How does rotation act on this? So the rotation, so under rotation, how will you decide how rotation acts on it? In fact, you can go back to transformation of the metric. Let me write in terms of BU first. Okay, I'll just write Ij, okay, because rotation really acts in the spatial directions. So this is right. If we just make a transformation in the spatial direction, this is the way the metric will transform. Okay. And if we want rotation in the 1-2 plane, for rotation in 1-2 plane, we basically take this matrix to be MIK. Okay, where M is this matrix. M is this matrix. Is this clear? Right, because you are trying to make apply a transformation that represents rotation around the third axis. Right, so that's this matrix. So it basically has only the 1 and 2 components. Right, the third component, the otherwise it's just identity matrix. Right, in the other blocks. Okay, so M to begin with is a 3x3 matrix, but it's like 1 0 0. Sorry, it's M and then 0 here, 0 here, and 1 here. Okay, as a 3x3 matrix, it will have this structure M and then 2 rows 0, 2 columns 0, and then 1 here. Okay. But in any case, so what I can write, so this equation can be written as E prime is equal to M E eta M transpose. So this is the important equation. Okay, because this is M, it multiplies G. Okay, G I am thinking of G Ij is eta Ij plus H Ij. Right? Eta of course remains invariant on rotation anyway. Right? So M eta M transpose is just eta. Okay, so you don't have to worry about that. So only the H transforms, right? And H in momentum space is the C. So now we have to ask, okay, that we choose E such that M E M transpose is equal to some function of theta times C. This is what one means by an eigenstate. That the effect of applying this rotation should give you back E up to some multiplicative factor. Right? Here it was a multiplication by a matrix, right? So it's the standard eigenvalue equation. Right? Here the transformation is like this. Okay, and as a result, transformation is like this. So what we demand is that this is equal to some function of theta times C. Is this clear? Okay. So I'll give you the answer. So exercise, check that for E equal to 1 Okay, it's a set of linear equations, so you can easily solve for what E should be. And what you can show is that if you choose E to be this, okay, if I have given the answer, it's easy to check, right? Take this form for E, right? Just substitute here, left hand side, and you will find that we get a matrix which is again proportional to E. The constant of proportionality is E to the plus minus 2 I theta. Okay. So these are the circularly polarized gravitational waves. Okay, if you choose E12 to be I times E11, okay, then it's circularly polarized in one direction with eigenvalue 2 I theta, E to the 2 I theta. If you choose E12 to be minus I times E11, then the polarization in the opposite direction. Okay, eigenvalue is E to the minus 2 I theta. So one important distinction between gravitational wave and electromagnetic waves is the eigenvalues. Right? You can see that here the eigenvalues are E to the plus minus I theta. Here the eigenvalues are E to the plus minus 2 I theta. So the eigenvalues of the gravitational wave are as if you have rotated by twice the amount. In quantum theory, this is related to the fact that when you quantize a gravitational wave, right, you get gravitons, they have spin 2, okay, as opposed to quanta of electromagnetic waves, the photons, which have spin 1. Okay, so the reason that the quanta of gravity have spin 2 is basically encoded in this 2 over here. Yes, exactly. Right. So when you look at the eigenvalues of the rotation operator, right, you see what eigenvalue you pick, and that tells you what the spin is. Right. If you see to the plus minus I j theta, then j is the spin. Okay, that's not obvious from whatever I have said, right? But the statement that the eigenvalues are e to the plus minus 2 I theta is a purely classical result. Any question?
Here it comes from the fact that it has two indices, so that's why the matrix multiplies twice. And
that's that, yeah, yeah.
So how is that related to gravity having spin? These two facts are also gravity having spin 2 and G transforming as.
Yeah, true, but it's really reflected here, right? Because if you had an antisymmetric spin 2, for example, you could have taken an antisymmetric tensor, right? Then the result will be different. Okay, the fact that you have a symmetric tensor is important. So just having multiple n indices doesn't mean that it will be spin n, right? If it's completely symmetric spin n, symmetric tensor of rank n, right, then it has spin n, right? But not otherwise. But the real information is here, right? What happens under rotation? That if you have a plane wave propagating in certain direction, right? How does that change when you rotate around that about the axis of propagation? Okay, so from next time we are going to start discussing cosmology, which will be the last major topic. But to do that, we need some technology. So what I plan to do in the rest of today is to describe some of the technologies that we'll be using. Okay? And these are in fact general technologies, not necessarily tied to cosmology. Okay? And in fact, we have implicitly used them in the past, right, in various analysis, but we'll try to formalize it because it will be useful when we discuss cosmology. Okay. So the notion that you want to discuss is the notion of isometries, right? And I think I have mentioned it and you have also seen it in various contexts. Okay, but let me just give the formal discussion of what one means by isometry. So let's recall that the general coordinate transformation is G prime mu nu of x prime okay, this you can this is there for any arbitrary space time. We'll say that the transformation is an isometry if G prime mu nu of x prime is equal to G mu nu of x prime. Okay, or you could have written it as G prime mu nu of x is equal to G mu nu of x for all x prime. So the argument is just a dummy argument. So isometries are special kind of general coordinate transformations which preserve the functional form of the metric. Okay, the new metric has exactly the same functional form as the old metric. Is the definition clear? Okay. So this we have seen before. So let me just remind you. So recall the Schwarzschild metric. So well, I'll write down the starting point because that's where the isometry was manifest. Okay, R was given by square root of x1 squared. So let's discuss some isometries of this. So consider the transformation T prime, which is T plus C, and x prime equal to x. C is some constant. So if you make this transformation, right, and rewrite this in the x prime coordinate system, then ds square becomes minus okay, it's trivial. All that I have done is that dt I can write in terms of t prime because dt is dt prime. Okay, I have written that. And for rest, okay, x prime is equal to x anyway. So I can just rewrite everything in terms of the prime variables. Okay, and this by definition is g prime mu nu of x prime dx prime mu dx prime mu. Okay, and so from this you can read out what G prime mu is. And so the claim is G prime mu nu of x prime is equal to G mu nu of x prime. Is it true? True or not true? True. Okay, let's just check one. G prime ij of x prime. So what is this? The formula for this. Something is wrong here, I think. I think there's a dt prime here. Yeah. Yeah, dt prime. Thank you. Yeah. Anyway, so this doesn't matter. Okay. So what is G prime ij of x prime? Ij component for the matrix. F4 R prime x prime j x prime I x prime j. Anything else? F3 R prime F3 R prime delta ij. Right? Let's look at this. What is Gij of R? Gij of x. Same thing without the prime. So F4R xi xj plus F3R delta ij. Right? So we see that G prime ij of x prime is if you take the expression for Gij and replace x by x prime, take the expression for Gij and replace x by x prime, you get G prime ij of x prime. Is that clear? So this is trivially an isometry. Okay, but not all metrics have this isometry. If there is a time dependence, this will not be true. Right? So it is trivial and isometry, but yeah, I mean it's not always the case that this isometry exists, right? So isometries are special properties of the metric that you are dealing with. Right? Some metrics may have no isometries, some metrics may have a lot of isometries. Is it clear? So for the same background, same metric, we can consider other isometries. So if we take t prime equal to t and x prime equal to x prime I equal to r ij xj, where R is a constant matrix with R transpose R equal to 1, identity matrix. This is also an isometry. Right? You can explicitly check. Okay, I can write this other way. Xi equal to Rij x prime j, because it will be easier to calculate this, right? If you substitute xi equal to Rij x prime j here, right, then each of these can be this becomes x prime dot dx prime, right? Because R transpose R is 1. Similarly, this becomes dx prime square, and this becomes again x prime dot dx prime, right? By the fact that R transpose R equal to 1. So the metric has exactly this form. Okay, the metric in the prime variable will have exactly this form, and that means that you have an isometry, right? Because this is the original metric with the variables replaced by the prime variables. So the symmetries of the Schwarzschild metric that we had seen are isometries. But when you think in terms of isometry, one feature of this is that the existence of an isometry doesn't depend on the choice of coordinates. The way we had introduced Schwarzschild metric, right? We said that we'll impose the symmetries by saying that there is a choice of coordinate system in which there is a time coordinate and x1, x2, x3 coordinate, in which the metric looks time transition invariant and spherically symmetric. But when we state the result in terms of isometries, the existence of the isometry doesn't depend on the choice of coordinate system. I can take a completely different coordinate system in which nothing may be visible, but the matrix will have the isometry. Right? This is what we'll see this a little later. Right? How we get there. This is not. No, constant matrix. Yes, so this is constant. The same isometry I can write in a different way, in which where it acts differently at different points. Yes, meaning it will not be the number of parameters will be finite. If you are asking whether there can be isometries where the parameter is a function of x, that's not possible, because given a manifold, given a space, right, there is a maximal number of isometries you can have, okay, and that's a finite number. Okay, I think the maximum, if you have an n-dimensional space, right, I think the maximum number is n into n plus 1 by 2 basically. Okay, in an n-dimensional space, this is the maximum number you can have. So you cannot have a function of what of isometries, if you're asking, but the form of the isometry transformation certainly could look like, can be made to look like that they depend on space-time coordinates. Yeah, this is the maximal number of isometries you can have. This is not obvious to prove. In a d-dimensional space. Number of isometries is number of independent parameters that label the isometry. So for Schwarzschild, for example, the number of isometries is a key. Time translation is 1, right? That's an independent parameter. And this rotation matrix, 3x3 rotation matrix has 3 parameters, right? The 3 Euler angles. So the number of isometries here is 4. Okay, which is still less than the maximum number you could possibly have in 4-dimensional space-time. Okay, is this clear? Yes.
But if you make some general transformation,
Yes.
then it may not be true.
It will still be true. Take the Schwarzschild metric, right? So for the terms, take the Schwarzschild metric. I make a general coordinate transformation. Write the Schwarzschild metric in a defined coordinate system, right? The claim is that it will still have isometries.
So these conditions that we said, time translation and this time translation and this rotation, these are not anticipated.
Yeah, so these, it will not look like time translation and rotation, okay? But there will be exactly 4 isometries in any coordinate system. Okay, maybe that's confusing. Let me write that down first, right? How to construct isometries in a general coordinate system. Okay. Okay, so let's suppose x prime mu equal to f mu x is an isometric. Okay, which means if you replace x prime mu by f mu x, the metric retains its form. Okay, the functional form of the metric doesn't change. Now, I describe the same metric using a new coordinate system. You introduce a new coordinate system. Y mu equal to say phi mu of x. Okay, let me introduce shorthand notation because it will be useful. So this, I'll use a shorthand notation. This kind of transformation, the shorthand I'll use as x prime equal to fx. Okay, it's understood this is a vector. This means that f is actually a vector. Okay, but it will be useful to write this. Similarly, here I am writing y equal to phi x, but this really means that y mu equal to phi mu x, right? This is a coordinate transformation I am making, new coordinate system. And phi is not an isometry, not necessarily an isometry. So the metric you can rewrite in the y coordinate system, right? Which has a different functional form because phi is not an isometry. Now the claim is that that metric has an isometry. Okay, that means that there is a transformation on y, okay, which is an isometry of that metric, okay, and that transformation is the following. That so let's suppose that this gives you g tilde mu nu of y is the new metric. Okay, that you get by making this transformation, right? So this is by construction del x rho del y mu del x sigma del y mu 0 sigma of x. So the claim, I'm not going to prove this, but it's more or less straightforward. You just have to do some algebra. That g tilde mu nu of y has an isometric under the transformation is y prime is phi of f of phi inverse. Phi inverse is the inverse transformation of phi, right? If y is equal to phi of x, x is equal to phi inverse of y. That's the definition of phi inverse. So what are you doing here, right? So in y coordinate system, we knew that in x coordinate system there is an isometry. So phi inverse y basically takes you back to x coordinate system. Then you transform by f. That's an isometry in the x coordinate system. Right? But you want to describe this in the y coordinate system, right? So then you transform it back using phi coordinate. So this combination of three functions will be an isometry in the y coordinate system. Right? So you can start with Schwarzschild metric and make a complicated coordinate transformation where nothing is visible. Right? It doesn't look time translation invariant or it doesn't look spherical symmetric. Nevertheless, the fact that the original metric had time translation invariance and spherical symmetry, right, is very much encoded in the new metric. Okay, it's that the transformations are not obvious. Okay, but if you want to find the transformation, you can just compose this, and that will give the transformation. What particular isometry it has. Is this point clear? Yes. So our isometric group is a subgroup of general coordinate transformation that is an invariance of that keeps the form of the metric unchanged. Right. So isometric group could be just identity element. Right. It may be just trivial. Only identity element may preserve the metric. Not every metric has isometry. But the metric having an isometry is not a coordinate dependency. Right. If it has isometry in one coordinate system, it will have isometry in all coordinate systems. So it's an intrinsic property of the metric. Any question? The second statement, which is again reasonably straightforward to see, is the isometry forms a group. Okay, you can again try to verify all of these explicitly doing some algebra, right? But the statement is obvious. And so what do you mean by it forms a group? Okay, let's suppose that x prime mu, x prime equal to fx is an isometry. Let's suppose that also f prime equal to hx. Why should we do h? Okay, doesn't matter. H is not the same as hij. Okay, h is some function. H mu, if x prime equal to hx is an isometry. Then x prime equal to f of hx is also an isometry. Okay, this is basically the statement that if the first transformation doesn't preserve the form of the metric, okay, then you can apply the first transformation and apply the second transformation again. It will also preserve the form of the metric. Right? So the combined transformation preserves the form of the metric. Okay, so this is the sense in which it forms a group. That if we have two isometries, then their composition is also an isometry. Is it clear? Exactly. N into n plus 1 by 2. Yeah. So if it's an n-dimensional space, right, the order of that group cannot exceed n into n plus 1 by 2. And in fact, the maximally isometric, maximally symmetric spaces, right, which is where this is saturated, are all classified, right? So if you know that there are n into n plus 1 by 2 isometries, then you know what the space is. Well, you don't know what the space is uniquely, but there is only a finite number of choices. Pardon? For the metric, yes. Okay, for example, if you are dealing with 3 dimension, okay, 2 dimensions, right, and you have the maximally isometric space, right? So that's in 2 dimension, the number is 3, right? So there are only a limited number of spaces which has that isometry. Can you count? Which are those? 3 isometries in of 2 dimensional space. Yeah, but what are the spaces? Yeah, so R2 is what? Plane. Plane has how many isometries? 2 translation, 1 rotation. Right? You can translate in x and y direction and you can rotate in the xy plane, right? The sphere has S2, right? How many isometries does it have? 3. 3-dimensional rotation, right? SO3. Yeah, I mean, it's not visible perhaps, right? If you write in theta phi coordinate, but it actually has 3-dimensional rotation, right? 2-dimensional sphere is the surface of a 3-dimensional ball. And then H2 is a little more complicated. It's a hyperbolic space, right? That also has 3 isometries. Okay, instead of having the group being, instead of SO3, you have what is called SO21. Okay, with there's one minus sign in the transformation now.
How is the case for the sphere?
No, but there's an Euler angle, no?
Oh, okay.
Yeah. So I mean, so there are 3, and that so SO3 rotation parameterized by those 3 Euler angles leaves the sphere unchanged, takes a point on the sphere to another point on the sphere. Yes, indeed. Right. In Euclidean space, it's true. This is the story. If you have Lorentzian signature, right, it's the same story, but the spaces are a little different. But fortunately, we will not really need the Lorentzian case for us, for our purpose. Something like, yeah, exactly. Okay. Now let me say something about infinitesimal isometries. Again, this is something that we had encountered earlier, but perhaps I didn't say it in the language that we are using now. So as the name suggests, these are isometries that correspond to infinitesimal transformations, right? Transformations that are close to identity. Okay. So let's suppose the transformation is x mu. Let me put the sign correct. X mu equal to x prime mu epsilon times I mu, where epsilon is small number. Then we have this relation, the g prime mu nu is of x prime is this is so far general coordinate transformation, right? I have not imposed isometry anywhere. So this will be given by delta rho mu plus epsilon times del prime mu 0 times delta sigma nu plus epsilon del prime mu I sigma times 0 sigma, which I can write as, if we expand it out, g mu nu of x plus epsilon so the first term is this times this times this. That's what we are using. So you have to pick only one part of epsilon, right? So epsilon times del prime mu 0 and 0 sigma. So sigma becomes nu 0 nu of x plus epsilon del prime mu I sigma, and now we pick the delta rho mu from here. So g mu sigma. Okay, so far it's just general coordinate transformation. So this I can write as G mu nu of x prime. Yeah, I'm going to do a Taylor series expansion because x is x prime plus epsilon xi mu plus epsilon and then all of these. Yeah, I'm expanding x around x prime, right? Oh, this one. Oh. Which one? Oh, yeah. Okay. Thank you. Is this clear? So this is just a general coordinate transformation law of G, right? Because I have taken G mu nu of x and just Taylor expanded around x equal to x prime. Now we use the fact that for isometry we need G prime mu nu of x prime equal to G mu nu of x prime. Right? So this should be equal to this. Yes, all of the terms are evaluated x prime. Actually, here it doesn't matter. No, this is evaluated x prime, this is evaluated x. But as we'll see, it doesn't really matter because x and x prime differ by order epsilon, right? There is already an order epsilon here. Okay, so on the right hand side, now I can just say, replace all the prime by unprimed variables. So this tells us that is this clear? We replaced x prime by x since they differ by order epsilon. Okay. And now it's a simple exercise to check this gives just have to organize the terms appropriately. Right? These derivatives of g and combined with all of these, right, can be just written in this way. Okay, the symmetrized covariant derivative of psi is equal to 0. Is it clear how to do this? Right, you basically use the definition of the Christobel symbol, right, and work this out. I mean, here, for example, this is already derivative of g. Here, to get to this form, you have to write this into the derivative of the whole thing, right? That will lower the xi index, but then you have to subtract the derivative of g. Right? And similarly, they are using that, you will find that it can be organized in this form. So these are known as killing vectors. Okay, so the existence of continuous isometries, right, lead to killing vector because infinitesimal version of those is generated by the killing vectors. Okay. And once you put it in this form, okay, it becomes obvious that the existence of isometry, at least the existence of infinitesimal isometry, is independent of the coordinate system you choose. Because suppose you have an isometry, right, written in some coordinate system, you have gotten the killing vector. Now you go to a different coordinate system, right? And you have to ask, is there a killing vector there in that coordinate system? All you have to do is that you just transform xi. Right? This is a covariant equation, right? So if you go to another coordinate system, right, transform xi as a covariant vector, it will continue to satisfy this in a new coordinate system. Right? So if a killing vector exists in one coordinate system, it exists in all coordinate systems. Right? So that's the same statement that we saw earlier, that the existence of isometry doesn't depend on the choice of coordinate system. Okay, even though the form that it takes may differ. Okay, some coordinate system may be specially designed to make the isometry manifest, right? But doesn't mean that in a different coordinate system isometry is not there.
Such that a mu sigma at x prime is equal to a sigma at prime x prime.
Yes.
So we'll get some equation.
Yes.
Like are they? I mean, this is whatever we have done for metric can be done for any tensor set. Are they important or like?
They are important in the sense that I mean, even rank 2 tensor, T mu nu, for example, right? If a space time has the certain isometry, right, then T mu nu you also expect will be invariant under that transformation.
Because everything will be same, just G in exchange by.
Yeah, but the question is, okay, could you have put a T mu nu which doesn't satisfy this relation? Suppose G mu nu satisfies the relation, but T mu nu doesn't. Is it possible? For T mu nu, it's not possible. The reason that it's not possible is because T mu nu appears on the right hand side of Einstein's equation, right? You can show that if G mu nu has isometry, right, then R mu nu minus half R G mu nu also will have the isometry, because those are after all tensors constructed out of G mu nu, right? So if G mu nu has certain symmetry, R mu nu better have that symmetry, right? So if Einstein's equation has to hold, T mu nu better have that symmetry. Right? The reverse is not completely obvious, but it's also more or less true. That if you have a matter distribution, T mu nu, right, which has certain isometry, right, which means that under a coordinate transformation, it preserves its form, then it's very hard to imagine that the G mu nu doesn't have that isometry. Right? The R mu nu minus half R G mu nu has that isometry clearly. Right? And typically you would expect that that can only happen if G mu nu also inherits that isometry, right? Even though it's not a foolproof argument, because it could happen that G mu nu doesn't have certain isometry, but when you take derivatives and take that combination, it acquires a symmetry. Okay. Any question? Okay, so this is as far as we'll need to know about isometries. Now let me explain why is it important for cosmology, right? What we do in cosmology. Okay. So cosmology is basically the study of the whole universe. Now, when you say study of the whole universe, right? I mean, of course, you cannot solve the Einstein's equation for the whole universe, right? Because whole universe is a complicated matter distribution. Okay. So you have to simplify the problem, and the way we simplify it by taking averages over large distances. Okay, that you don't try to study, for example, when you take say study of the universe, Right? We don't try to take into account the fact that there are solar system in this region and then empty space in another region and so on. Right? We try to work at a large scale by taking averages over large distances. And it turns out that when you take averages over large distances, there are certain symmetries, okay, certain features that emerge, and this is known as homogeneity and isotropy. That the universe looks homogeneous, right? Which means that if you take, say, average of the density, right? Take the matter density in some region, take matter density in some other region in the universe, right? They look the same. Okay, they have more or less the same value. This is a feature which is called homogeneity. Isotropy is a feature that if you look in different directions, then the matter density again looks the same. Okay, that if you look in this direction, you see certain matter density, you look in another direction, you see certain matter density. And it's not just for matter density, everything that characterizes the universe seems to have this property. Okay, so this we have to encode in our description of the universe. Okay, the fact that there is this property of the universe where when you take averages over large distances, you find that the matter distribution is uniform in all directions and it's isotropic. Now, there is one distinction that you have to make between the homogeneity and isotropy, right? Now, normally you would have thought, okay, if it's homogeneous, then it's also be isotropic, right? If it's the same in all directions, then of course it should be also, if it's same everywhere, it should also be same in all directions. But in general, because you have not just scalars, but also tensors and vectors, etc., that characterize the state of the universe, this is not always true. So here is a simple example of a universe that is homogeneous but not isotropic. So imagine a universe which has a electric field, uniform electric field, right? It's homogeneous, right? Same everywhere. But it's not isotropic. If you look in different directions, you will see different physics, right? If you put an electron, it always tends to move in one direction. So here is an example of a universe that is homogeneous but not isotropic. The reverse also you can do, right? Isotropic but not homogeneous, right? I mean, let me give a two-dimensional example. So suppose I have an ellipsoid, right? And you are sitting at the top of the ellipsoid. If you look in different directions, right, it will look isotropic, right? In whichever direction you look, it looks similar, but it's not homogeneous. Right? The ellipsoid has strong curvature in some regions and weak curvature in other regions. So the homogeneity and isotropy are two different properties, right, that you have to impose. Okay. Now the second feature that we have to keep in mind is that the universe doesn't have time transition symmetry. Because I mean, this was discovered more than 100 years ago that the universe is expanding, okay, which basically means that different objects in the universe are just moving away from each other. So it's not time transition invariance. Different times the universe looks different. Okay. So this means that when you talk about homogeneity, you have to specify homogeneity at the same time. Now this seems to run counter to whatever you have learned, right? What do you mean by homogeneity at the same time, right? How can you compare time here with time there? But when you describe the universe, you have to do that. And that you do that because it's not just a consequence of general relativity, right? In general relativity, indeed, there is no time. Okay, there is no preferred time. But the universe seems to have a preferred time. So that when you say that the universe is homogeneous, that for fixed value of that time, the universe looks the same everywhere. If you look at a later time, okay, universe will look different. Okay, so this is again, so universe has some intrinsic time that you can call cosmic time, that is special. Okay? Now, of course, once you write the equations in that coordinate system where that intrinsic time is there, then you can, in principle, you can go back to any other coordinate system. Right? The physics will not change. But there is a preferred time coordinate, so that a fixed time slice, the universe looks homogeneous and isotropic. no meaning, write it as t, right? You define t as the time coordinate, right? Now, if you want to know, okay, what is the operational definition of the time coordinate, right? I mean, here is the following, here is a possible operational definition. Okay. It's the coordinate, time coordinate, so that at fixed time, there, okay, first of all, probably not, this is not familiar to everybody, that the universe has this cosmic micro background radiation. Okay, that you see this 2.73 degree Kelvin background radiation that fills the universe. Okay. But this temperature changes with time. Okay, earlier it was hotter, later it will be cooler. Okay, so this cosmic time you define such that at fixed time, okay, that corresponds to some space like surface, right? The micro background temperature is the same everywhere. That is the definition of the cosmic time, right? That you can take as the operational definition of the cosmic time. Okay, but for us, okay, we'll just say that there is a cosmic time, okay, and at that fixed value of the cosmic time, the universe looks homogeneous and isotropic. Okay. Now, given this, we have to ask, right? Then, what is the most general metric given this criteria? Okay, because you want to start. Yes.
When we observe any object in the universe far away, we are observing in the past, the object as it appeared in the past.
Yes.
So, you know, observe the time that we are considering that is something.
Yes, indeed. So
we are measuring distance only.
Yeah. So the point is, it is true that when you look far away, right, you are looking in the past. So when you say that it's homogeneous, right, you have to reconstruct what the state of the universe will be today, right? You have to evolve it forward and see what it will be today, right? And that is what is uniform, right? Otherwise, in the past, indeed, the universe, I mean, if you just naively look in the different parts of the universe, right, and try to see if it's homogeneous, you will not find that it's homogeneous, because in the past, the density was more.
So then the velocities that we calculate, that we observe, the galaxies are moving upon and how are they calculated? Are we calculating? I mean, those speeds are in the past.
Yes. So you have to reconstruct, right? So you make some observation, right, and then you put in your equations to reconstruct what the velocities would have been, right? It's not that you directly observe the velocity and that's it. No, that interval is not, cosmic time is not the interval, it's a particular coordinate size, right? That imagine that you have your space time. Suppose you have your space time and you have chosen some time coordinate, right? Okay. Let me say this is not a cosmic time, this is some general time. In this general time, right, if you draw a fixed time, constant time surface, right, you will find that in different regions, the densities are different, or micro background temperatures are different, right? So then this means that this is not the correct definition of the cosmic time. Okay. So what you do instead, that you take this general time, okay, and then you draw a surface again. So that the cosmic micro background temperature is the same on this surface. Because at every point, right, the cosmic micro background temperature is decreasing, right? So you see at this general time, as you go, this is the space direction, right? As you move in space, as you go to different points in space, right, you choose a point where the temperature is some fixed number, right? Where you started from here, say. You will get a slice. Right? Now you have to make a change of coordinate, right, where this slice, okay, corresponds to t equal to constant. Right? The new coordinate must be such that t equal to constant describe this slice. And you have to do it for all slices like this, right? Fixed micro background temperature should correspond to fixed t. Right? That you can take as a definition of cosmic time. Yeah. So no, this is I have just drawn, right? In t equal to constant, so in the t, if you really use the cosmic time, right, then this will be just straight, right? Because the temperature is same everywhere. That's the definition of fixed cosmic time. See, detector will not get that. You have to choose your time coordinate first. Only then the detector will get that. Because I mean, if you place a detector here, right, at fixed time, you have to fix a time coordinate and then say a detector here and detector here measures different temperature, right? Which means that this is not the cosmic time. Okay? So cosmic time by definition should be chosen as the constant t slices, right? In fact, you can, I mean, you can use the temperature of the microwave background as a definition of cosmic time. Because then by definition, right, at fixed cosmic time, the temperature is the same, right? Because you put a detector on the earth and detector at the moon, right? You see at what time on earth the temperature reaches 2.73 K. You see at what time on moon the temperature reaches 2.73 K. You declare them to be the same cosmic time. Okay? Those intervals you say that they are happening at the same cosmic time. Yeah. So the point is the fact that the CMBR is homogeneous, right? That happens only in this particular choice of time coordinate. That you have to first choose a constant time slices. See, because otherwise, if you don't even, I mean, if you haven't fixed your time slice, right? What do you mean by same time? Then the notion of homogeneity doesn't exist, right? I mean, if you use this general time, right, where the cosmic background temperature is like this, it doesn't look homogeneous because the constant time slices, right, there will be different temperatures in different parts of the universe, right? So you have to choose a specific time coordinate, right, which, as I say, you can take to be the temperature itself, right? But at every point, temperature is decreasing as a function of time, right? So temperature is a proper measure, is a good measure of the cosmic time. Thermal clock, right? But you can use other clocks also. Once you have fixed that, right, then the claim is that the matter distribution also becomes uniform, right? If 2 points have the same microwave background temperature, they also have the same matter density, right? So the uniformity, right, once you have fixed your cosmic clock, right, everything is uniform, almost uniform, right? There are fluctuations that will, that will probably be not discussed in this course, but in the next course. But up to that point, you can say that the cosmic time is something that makes everything uniform, right? Including microwave background radiation and matter density. Yes. Yes, indeed.
So when are we doing the average before thermal clock or after?
Exactly, right. So it goes simultaneously, right? You have to choose a thermal clock. That statement is that there exists some clock, right, such that at the same time that the matter density is uniform. So that clock, let's say I say that you choose as a thermal clock, microwave background temperature, right? You take, so you declare that the time here is equal to time there if they are, as long as their temperatures are the same. Then you do an averaging, right, over a slice near this region, right, again at fixed temperature, right? choose the slice so that the temperature is the same everywhere. You do an averaging there, right? Choosing the slice so that the temperature is the same everywhere. And then you find that the average densities are also the same. Is this clear? Yes. Yes.
And in that case, like you're looking at each and every point. For example, like you said, Earth and Moon. And for that matter, I can talk about Bangalore and India.
Yes.
In that sense, why we need homogeneity and the very large scale. Because we already, there is no need for.
Yeah. So to fix the cosmic clock, there is no need, right? But to be able to solve Einstein's equation, right, we need. I mean, otherwise you have to take into account the fact that there is Earth here and then there is a sun there and then there is Jupiter somewhere else, right? I mean, you cannot solve the Einstein's equations analytically with such complicated matter distribution, right? So you need the averaging to be able to solve the Einstein's equation, right?
Say for example, I'm taking.
You are taking?
I just wanted to solve Einstein equation.
Okay.
In that case, I don't need any kind of homogeneity and isotropy.
No, because vacuum is homogeneous and isotropic anyway. T mu is 0, right? So yeah, you don't need, but you have it if you use vacuum.
But whatever the source, I mean, all the sources which is providing the curvature in space-time, which is there, but I'm liking the gravitational situation. There is a source, but I'm not looking at the source, I'm looking at far.
But in the universe, right, there is always source. Because there's a matter distribution, right? So you cannot go away from the source. So you have to deal with the fact that you have source present everywhere, right? And you have to solve for the metric, right? And that, I mean, in principle, you can do for any distribution, right? The Einstein's equation is there.
But my confusion is that because we choose the time coordinate such that every point is sort of equivalent because we are measuring the same CMB temperature, same density.
Yes.
In that case, this TMU you should simplify.
It will.
Yeah.
I mean, you want to simplify it.
We have to deal with a very complicated matter because we are defining with a uniform matter distribution.
Oh no. Wait. Uniform CMB temperature. Fact that uniform CMB temperature implies uniform matter distribution is not guaranteed, right? That's the statement of homogeneity and isotropy. That once you have fixed the temperature, let's fix the temperature by time by saying that the uniform CMB temperature at fixed time slice. Okay? Then you have to ask how does the matter distribution look in that coordinate system, right? And that is homogeneous and isotropic.
And for that you need the large scale average.
Yeah, for that you need the large scale averaging. Right? The CMB temperature in Bangalore and Cochin may be the same, right? But the average densities, right, are not the same around these two cities, right? So for that you need the large scale averaging. Yes. Say, yeah.
But these slices cannot be very good. There's no guarantee that all the slices, the temperature, the isothermal.
Whatever, yeah.
There's no guarantee they will all look the same. So somewhere it can be some close thing and somewhere.
Yeah, in general, but in the universe it doesn't happen. In the universe, I mean, once you impose a condition for homogeneity and isotropy, right, the form will be fixed. Right, we will see what form it takes. Right? So basically, you have to use the isometry, right? Given this physical input, that you have homogeneous and isotropic universe, right? In this sense, that the fixed time slices are homogeneous and isotropic. Then you have to ask what is the most general metric, right? And for that, you have to use this notion of isometry, right? How you formalize this notion that it's homogeneous and isotropic, right? And then ask what is the most general metric that satisfies those formal criteria. Okay, so tomorrow I think there is a tutorial, right? So the class will be next week. Well, I mean, what infinitesimal axiomatic are used, for example, because it's much easier to do differential equation than general term. We will classify maximum by saying that there should be n into n plus 1 by 2 dependent solutions.
So that will equation. I can given a metric, I will have to validate it. And I can always find Z graph. Right.
You may not find it exact.
Yeah. There may be no solution. But yeah, solution. And how will that?
The point is that by dividing that there will be n into n plus 1 by 2 solution
Oh,
to this equation.
yeah.
Constant on x.
Oh, this, okay. It's the other way around.
Yeah.
We'll have xi and we will try to get I mean consider the form of the metric.
I'll not do that, but that's the way you classify. When you demand that there will be maximum number of size possible, right? And then you can ask what kind of metric has that.
One question again, why are we interested? Isn't it less constraining than having a general?
Usually not, because once you have the infinitesimal generator, right? You can build the finite transform, right? Infinitesimal ones are, as I said, easier because differential equations are easier to deal with generators.
Okay.
But here the mathematical problem is that we are looking for rate, right? For which this equation has n into n plus 1 by 2. Those cases then can be classified.
I may not be able to get some equation.
Yeah, for finite transformation, yeah, you can get some equation, but it's hard to see how to use them.
The definition is start from the main equation. That is the main equation.
Yeah, yeah, exactly.
Yeah. But yeah, okay. So we are sort of using the fact that it can say follows that equation under a finite game, and it will certainly be.
Yeah, it is a continuous symmetry.
Yeah.
Then if you have this finite transformation, they are also limited. Yeah, of course, the group is one of the right? So you cannot say that you will form an identity of all the generators, but you take the maximum number of commuting generators, and you can ask that they will have eigensets of those. That's the closest you can go to factor.
So these are in card.
So when you say go back to polar coordinate, eta mu you run it right in the polar. Okay? So then eta mu plus h mu transform this to polar coordinate, right? And then subtract out the background. Whatever eta mu becomes a polar coordinate. That will be h mu in the polar. So del mu's will be covariant derivatives. The covariant derivatives are ordinary derivatives written in polar. See, the ordinary have intermediate plus HEV, right? And transform to a general form and see what usually HEV satisfies in that form.
So this was basically my confusion yesterday also, and I did ask you that if but some general finite transform such that you also transform the eta as state. Then HEV will also transform like a general.
Yeah, but the background will also transform.
Background will
also
also
challenge for it.
So why don't we consider such thing when you discuss
If you are to describe HEV polar